So thank you all for being here today. This is one of our TCOptRob seminars. Just so you know, if you like this, there's more of them. We've got another one coming next month, another one in April. Please check out our LinkedIn email list, all this other sort of stuff, and we'll sort of keep you updated. Also, if you want to think into the future for the TC, we will definitely have some sort of social event at ICRA. Details TBD, sort of waiting on finalizing all of the other things going on so we can find a nice slot for that. But we hope to sort of see you all in Vienna in person as well. And I apologize in advance if you hear some screaming in the background. It is school vacation week, and so I have many a small child at home. Um, but I'll try to mute myself and let Thomas have most of the volume. So let me do a quick introduction for Thomas now, because we're very lucky to have him today. Dr. Thomas Liu from Toyota Research Institute is going to present on uncertainty-aware control at the limits. Thomas is a research scientist at TRI. He completed his PhD at Stanford and his master's at ETH Zurich and his bachelor's at EPFL. He had internships at Google Brain Robotics and at NASA JPL. His research focuses on the design of decision-making algorithms for autonomous systems using techniques in optimization, control, and machine learning. Thomas is a recipient of the Outstanding Paper Award at the 2024 Coral Conference, Student Paper Award at CDC, and also at Control Systems Magazine Outstanding Paper Award in 2023. Thomas is also just an absolutely wonderful person. I'm very lucky to be able to collaborate with him on some projects right now, and I'm really excited to hear him talk about all the things that he is doing. So thanks. Take it away, Thomas.
Thank you, Ryan, for the intro. You're great too. So hello everyone. So thank you all for being here today, and thank you again for the invitation to give this talk. So today I'm excited to present our latest research at TRI on uncertainty-aware control towards developing expert assistive driving systems. But first, I'd like to thank an incredible team of researchers and engineers at TRI, without whom I wouldn't be here presenting this work today. So I'll be presenting two works that were actually led by two interns over the summer, by Alexander Davidov and Emre Adabag. So today you'll see results on high-performance cars, and you can imagine that it takes an incredible team of people to maintain and develop these vehicles and the algorithms that run on them. So our team at TRI is doing research on driving at the limits of handling. And the reason is that by tackling challenging problems like autonomous drifting and racing, we better understand how vehicles behave at the limits and how an AI could potentially assist us on the road to make driving safer and more enjoyable. So for example, such a system could help us be better drivers in adverse weather, like when driving on snow or ice, or help us react to sudden obstacles on the road. So in the next video, I will show you an example of drifting using our Toyota Supra. And please say something if the sound is not coming out.
Giving an ordinary driver
whenever you're ready
the drifting skills of an expert.
So about once a month, we go to the racetrack and test our algorithms on our autonomous car platforms. So here we have the Toyota Supra that is autonomously drifting through the racetrack, staying on the track at all times, and the car is fully controlled using optimization-based techniques called model predictive control. So as you could see in this video, one challenge problem that we study to develop expert driving skills is drifting. So in short, drifting means operating the vehicle in a state of controlled oversteer. So as you can see here on the left, the vehicle is pointed at the cones, but is still following a smooth arc around it. Even though the vehicle is sliding sideways, expert drivers are able to control their vehicle in this regime. So today, the dominant approach for autonomous driving at the limits is model predictive control, or MPC. MPC uses a model of the vehicle to predict where it will go and select control inputs like steering angles and throttle commands to steer the vehicle through the racetrack. It's attractive because it's interpretable. It enables enforcing constraints like actuator bounds and staying on the track, and it works well in practice. So in today's age of learning, many robotics are reinforcement learning and imitation learning. Instead, we rely on MPC because it generalizes across vehicles and tasks. It allows encoding physics and constraints and works well with limited data. And we can always adapt models in real time to get good performance. So here you see a different Lexus LC500 vehicle that we drift through a puddle of water using very similar MPC algorithms by changing the reference and dynamics. So there are still challenges. So in practice, MPC with online adaptation is sometimes not enough. So for unstable systems, like for driving at the limits, small errors amplify quickly, and adaptation may be too slow to fix these initial control mistakes and recover control of the vehicle. Classical MPC plans using a single model that is assumed to be exact. So it doesn't explicitly reason about uncertainty and model mismatch. So here on the left is an example of drifting where initial errors amplify quickly and we spin out. Here is another one on the right where we race this Lexus vehicle through an oval trajectory, and there is a puddle of water that is not anticipated for, and the vehicle spins out. So as a result, MPC can fail when deployed in new conditions, which motivates a shift from point estimate control, where we use one model in the MPC, towards uncertainty-aware decision-making. So today, my goal is to present 3 different ways of using uncertainty for control at the limits. So I'll do it in 3 parts. First, I will present how we can learn a Bayesian dynamics model and use it to gather informative data. Second, I'll present new tools for accounting for uncertainty in MPC to be robust to model mismatch. And finally, I'll present a differentiable MPC tool that enables combining RL with MPC to do domain randomization and get robustness to uncertainty. So first, let me present some recent results on Bayesian learning and information gathering. So the problem we want to address is that sometimes MPC with online adaptation is not enough. So this is well known in the literature for at least 2 reasons. So first, our models are imperfect, and so errors will amplify quickly if the dynamics are unstable and nonlinear. So this means that we might quickly lose control of the vehicle, especially due to limited actuation. Second, it's known that unstable systems are difficult to simultaneously learn and control. So basically, if the dynamics are unstable, you don't have much time to make mistakes, learn your dynamics, and correct your errors to recover control of the car, particularly if you have limited control bandwidth. So if online adaptation may not be enough, a good question is, how can a vehicle autonomously gather missing information as quickly as possible? Especially because gathering this data can be expensive on such vehicles. So we have 2 main questions here. So first, what control inputs should we apply to best identify our uncertain dynamics? And by best, I mean as quickly as possible and to get reliable performance. And second, what do these information trajectories look like for driving at the limits? So the first component that we will use is a vehicle dynamics model that captures uncertainty. So in this work, we use last layer Bayesian neural networks. The idea is to parameterize the unknown dynamics G of the vehicle using a neural network. And we train the features phi and the last layer parameters by maximizing the log likelihood of a data set. Importantly, we fit a Gaussian distribution to the last layer parameters, which gives us an uncertain model. And the reason that we impose this structure is that then we really understand how uncertainty reduces over time as we observe data on the vehicle. Specifically online, given trajectory data and our prior distribution over the last layer parameters, we can apply Bayesian regression or least squares regression to compute the posterior over the data set and update our last layer parameters. So online, we will only adapt the last layer. We freeze the features, the neural network features, and this way we really understand how to adapt uncertainty online and do last layer posterior updates. And again, this structure allows us to learn expressive neural network features that will capture our dynamics and encode uncertainty into a meaningful latent space, quantify uncertainty over the dynamics through the last layer, and then update this uncertainty over time. So the next question is, how can we use this uncertainty, this uncertain model, for information gathering? So it turns out that for such models with uncertainty over just the last layer, we can write the one-step information gain from visiting a region of the state action space in closed form. And it's the first equation that you see here on this slide. And this equation means that we should visit regions of the feature space, so in the span of the features phi, that have high uncertainty. And so here on the right, you see a point that we selected that corresponds to high uncertainty states and controls. Then once we have this objective, we can plug it into an MPC or model predictive control formulation. So we can formulate an information gathering optimal control problem that encodes maximizing information gains, so finding information-rich data, while satisfying constraints like staying on the track and satisfying control bounds like engine torques being bounded, and same with the steering angle. So to summarize, the approach we're going for is a two-step procedure. So first, offline, we will train this Bayesian neural network, including the features and the prior distribution over the last layer parameters, theta. Then we freeze the features and we will online compute information gathering trajectories, execute them on the car, and adapt the last layer of our model so that uncertainty reduces. Finally, once uncertainty is small enough, after we've repeated this sequence a few times, we can deploy our model on the vehicle to get good performance on our task of interest. So the first question when we started this project was, what do information-rich trajectories look like for driving at the limits? So at the top here, you see a nominal driving trajectory. So here we see that the vehicle roughly drives straight, and we get such solutions from solving the problem without the information gain objective. So what does an information-rich trajectory look like? It turns out that if we solve our information gathering optimal control problem, the solver decides that the car should accelerate faster to gain informative data. Basically, accelerating and steering a little bit helps better learn longitudinal dynamics and tire friction limits. Then we can adapt our model on that data, and we found that uncertainty associated with velocity dynamics reduces a lot, especially compared to when using only the nominal driving data at the top. So we could stop here and deploy this on the vehicle. Or we could use this updated model to compute another information-rich trajectory and see what comes out of the solver. It turns out that if you repeat this procedure, you find a second information-rich trajectory that involves turning more aggressively. This makes sense because it will help us learn the rotational dynamics of the vehicle, and by reaching higher yaw rate values, for example. And when we adapt on this data, we find that uncertainty associated to yaw rate dynamics indeed decreased significantly. So now we have a model that used this information-rich data that we adapted on, and so we can deploy it on our challenging drifting task and see how it performs. So here the goal is to drift a figure-8 trajectory, and the top video shows what happens if you use the model that adapted on nominal driving data only, and you see that the vehicle is unable to complete the trajectory in this case. Whereas if you adapt on this information-rich trajectory, we get much better drifting results, and the Toyota Supra is able to follow this figure-8 trajectory pretty reliably. The most challenging trajectory that we evaluated this model on is the trajectory shown on the right here, which we call the tandem drifting trajectory because it was used in our tandem drifting demo, if you've seen the video on YouTube. So this one is particularly difficult because the drift initiation here is performed by the MPC, so you need an accurate model of the switch from driving grip driving to drifting to execute this trajectory. And it also involves multiple transitions, which are challenging. So you can see in red that even if we adapt our model over time, we eventually get good performance, which is good. So the method is working. But the problem is that the initial performance is really poor. So we see a large transient. The transient error at the start is very large. So it takes the car time to initiate the drift. And it's really these transient errors that we want to avoid to enable safety critical applications of this method, as they may involve avoiding obstacles that are close to us. And so in that case, large tracking errors might be impractical. Whereas our method, by adapting on a little bit of informative data, which is not even drifting data, we are able to get much more reliable performance. So to summarize, my first message is that sometimes online adaptation might not be enough, especially for unstable systems. And we can use uncertainty over our model in an MPC setting to get much more stronger performance by gathering informative data. Now, there are many interesting questions on this topic to pursue further. So for example, here we decompose the information gathering objective and this information sequence from the deployment, but it would be interesting to explore how to do both at the same time. So by exploring this question, then we would get into the topic of dual control, which is notoriously challenging, and even more so if we add constraints like staying on the track while doing this information gathering. Another question is how could we potentially retrain the features as well online? So this concludes the first part, where towards accounting for uncertainty, we use uncertainty to guide information gathering for driving at the limits. Now, I would like to discuss a different way to use uncertainty, which is to reason over uncertainty to select more robust control actions, which is robust control or risk-averse control or uncertainty over control. So first, let me show you an example. So here on the left, we're drifting around a circle, and the objective is to either avoid being inside of it or outside of it. And we see that a baseline MPC algorithm will drift very close to the constraints because it plans with only one model, and so it might be too optimistic and doesn't reason about potential errors. So drifting close to constraints might be unsafe or unreliable, and indeed, if we add model mismatch, then we might see poor performance in practice. In contrast, if we plan with 5 different models of the vehicle, so if we account for uncertainty over our model, then we can get much more robust performance. Immediately, interesting behavior emerges where the controller will drift further from constraints to be more robust to potential errors, or it might drift with a lower side slip to avoid spinning out and give itself more margin for error. So in this simulation here, you have a risk-averse MPC algorithm that plans with 5 different potential values of the friction parameters for the tire model and finds control actions that would work for all of these 5 different models. So these actions should be robust to potential different dynamics that would happen on the car. So this was for drifting. We've also validated these methods for racing tasks. So here the goal is to drift around an oval trajectory, and there is a puddle of water on the right, and you see that deterministic MPC will spin out after it hits the puddle. And the reason is that when you do racing, to go as fast as possible, you want to be always at the limits of your tire forces, which means that if you overestimate the forces that are achievable by your tires, you might spin out and lose the control of the vehicle. And this is what happens after you hit a patch of water, the tires get wet, you overestimate your tire forces, and you will spin out. So what people do in the literature is oftentimes they add regularizers in the cost, or they plan with lower friction values to drive slower and be more conservative. But these heuristics might be difficult to tune or take time to tune at least, and we sacrifice performance. Our take on this is that if instead we plan with a similar MPC controller, but with 10 different potential models of the vehicle, 10 different values of the friction parameters, we will automatically get additional robustness to this model mismatch. And we found in our experiments that we do drive more conservatively, so it's very important that we don't spin out, but suboptimality is reasonable in practice. So where is the research now? I think an important area of research is finding ways to solve these uncertainty-aware MPC control problems in real time. So in our group, we're pursuing two directions. The first one is to leverage GPU acceleration. So these stochastic optimal control problems, like I showed you before for racing, involve planning with multiple models. And so lots of the computations can be done in parallel over the models. So if you have a GPU, you can evaluate a lot of the terms and in parallel and come up with a solver that runs in real time, even though the dimensionality of the problem has increased. So I will not discuss this further today. I would like to present results on a different research direction, which is finding low-dimensional characterizations of the solutions. The idea is that if we know more structures about the solutions, then we can find fewer optimization variables to optimize over. So we reduce the search space, and so hopefully we can come up with algorithms that are real-time, very fast, but use and run also on computationally limited hardware. So before I can discuss low-dimensional characterizations of solutions, let me discuss optimal control. So in MPC, we often solve optimal control problems that look like this, where we minimize a running cost. We minimize this running cost, and we must satisfy these dynamics written as an ODE here. And so you see that the solution might look like this, where we converge to zero with the state, and the control is chosen to bring the state to zero and eventually gets to zero as well. So this is a classical optimal control problem. Now, what does low-dimensional structure mean in this setting? So oftentimes in optimal control, what we mean by solution structure is optimality conditions, basically equations that tell us what the solution should look like. So if a solution is optimal, what conditions must it satisfy? So in optimal control, these optimality conditions in continuous time are oftentimes characterized by a theorem that we call the Pontryagin maximum principle. What this theorem says is that if our trajectory is optimal, then there must exist an adjoint vector P that solves this ODE here with H the Hamiltonian. And this adjoint vector must end at zero, as you can see on the right here. And the control is given by the control maximizes the Hamiltonian here, H. So oftentimes in many problems, the control ends up having a closed form expression as a function of X and P. So the only the only unknown in these equations is the initial value of the adjoint vector. So this theorem really gives us a low-dimensional characterization of the solution, because from a problem where we look for the full trajectories over time, we end up with a problem where the only unknown is the initial value of the adjoint vector. And if we knew the initial value P0 here, then we would be able to integrate this coupled ODE, and we would know everything about the solution. These results are also used to find the full characterizations of the optimal solution. So for example, thanks to these results, we know that the solutions to rocket landing are bang-bang. So all that we have to find are the switching times where the control would switch from a maximum value to a minimum value and then back to a maximum value. So really, it's a much lower dimensional characterization of the solution, because we are looking for these 2 times now. Of course, I'm simplifying a little bit, but this is the takeaway, that these results can give us structure. Now, in practice, these tools are often used using a shooting method. So the idea is that we will guess initial values of the adjoint vector, integrate this coupled ODE forward, and the adjoint vector will not finish at 0. So then what we do is we run a Newton method or gradient descent on the initial value of P0 to bring it to the right value, so that when you integrate forward, you end up at 0. So this is a shooting method, and if it converges really fast, because we only optimize over P0. In practice, the 2 main limitations are that it's sensitive to the choice of initial guess, and you need to study these equations to derive a practical algorithm. But if it converges, it's really fast, and it leverages solution structure. So this is the deterministic setting. Now, what happens in the stochastic case? Or what happens when we add uncertainty? So in that case, we want to minimize the average of the running cost, and we have uncertainty, for example, characterized by Brownian motion, so like disturbances that corrupt the trajectory. And as a result, the solution might look like this, where the state roughly ends up at 0, but not exactly, because there is uncertainty. So it might overshoot, and it will not always reach 0. So this is stochastic optimal control. There are many different formulations, like risk-averse formulations. We can add fixed uncertain parameters in there, like uncertain friction parameters, and so on. So what does solution structure look like in the stochastic setting? So there is a stochastic Pontryagin maximum principle. What it says is that if we have an optimal solution, then there exists 2 stochastic processes, P and Q, and they solve this forward-backward stochastic differential equation here. And the control must maximize the average value of the Hamiltonian. So this is really good because it gives us structure. In particular, in the linear quadratic case, it gives us a full characterization of the solution, and there are many other applications. Now, the challenge is that in the nonlinear setting, in general, we don't have a closed form expression. The other issue is that we don't have with this theorem today a stochastic shooting method. In short, here we have 2 unknowns. We have P and we have Q. So we have, in a sense, fewer equations from these optimality conditions than we have unknowns. This is not surprising. The way the theorem is proven is in a way that gives us controls that don't look into the future. So basically the challenge mathematically, but it's a needed challenge, is that we look for controls that don't look into the future. Otherwise, we would not be able to implement them on the vehicle because we don't know the future value of the disturbance. But we still need to somehow encode optimality, which depends on the full cost until the end. And the final value of the adjoint vector must be 0. So we need to somehow formulate SDs that don't look into the future, that are not anticipating, but end somewhere. And that's why forward-backward stochastic differential equations were invented, exactly to formulate this desiderata, and this is the expected optimality result that we would get from using Ito calculus. Now, numerically, it's challenging because forward-backward SDs are difficult to simulate. And if you look at the literature, oftentimes how these methods are used in practice is using deep learning. So what you can do is you parameterize P and Q using neural networks, and then you will train the neural network until these optimality conditions are satisfied. So this works well, but for MPC, training a neural network might not be doable in real time, in milliseconds. So we cannot use these results to quickly replan in real time. So are we stuck? The idea that we used was to replace Ito calculus with rough path theory. The idea of the theory is to, instead of using Ito calculus to study these equations, we use rough path theory. So it enables us to study SDs pathwise. Basically, what you can do with this theory is say, if my control changed a little bit over this time interval, how will my sample path of my trajectory change as a result? And this is fully pathwise, just like in the deterministic setting. So it allows us to do math, to say, to derive error bounds and study how solutions change if you make small perturbations. And then, so everything is in a deterministic sense. And then at the very end, you can randomize and say, actually, my disturbances are random, my sample paths are random. So here is the stochastic element, and here is how you stitch back everything together. So rough path theory is actually a recent theory of stochastic calculus developed by Terry Lyons in the 1990s and actively studied today. It has many applications, including in deep learning and stochastic control. Now, so basically all we did was follow the proof of the stochastic PMP and replace Ito calculus with rough path theory as we go. And what we end up with is this theorem where we don't have the adjoint vector Q, we don't have this additional process, and all the information is in this pathwise rough stochastic differential equation. The only difference with respect to this deterministic setting is this additional term on the right. And if we can simulate Brownian motion, then we can simulate everything pathwise, like in the deterministic setting. So this is I think it's exciting because now we can come up with an indirect shooting method. So the idea is that if we approximate everything with Monte Carlo, then we can guess the initial values of the adjoint vector at time 0 and run a Newton method until they all converge at 0. And so as a result, if it converges, it's significantly faster than direct collocation-based methods because we don't need to discretize over time and only then solve the problem that's discretized and might involve a lot of variables, just like in the deterministic setting. So this concludes my presentation on finding new solvers to solve these optimal control problems under uncertainty fast enough. And I think that if we continue researching these uncertainty-aware control tools, we'll get MPC algorithms with in-the-loop domain randomization that will give us better performance. So I see I have 10 more minutes. So let me dive into the third part of the presentation that I would like to present today. So a third way to get robustness to uncertainty is via machine learning. So in robotics, this has shown really impressive results, and it's one of the go-to approaches, at least to get robust controllers. So people have trained RL policies encoded by black box neural networks to make robots walk by randomizing the environment, and the performance is really good, and we get robustness controller. Now, for us, for driving, we still want to retain some of the structure of MPC so that we can keep the inductive biases of MPC. So like if the reference trajectory or the task changes, we don't want to retrain the policy. So the question is, how can we keep the structure of MPC, its physics, its constraints, while making it trainable and scalable with learning? This leads to differentiable MPC, treating MPC as a structured policy class for reinforcement learning and other applications. Immediately, we face a challenge that is, again, computational. So MPC is solved by iterative optimization, which is sequential. Deep learning, on the other hand, scales by leveraging massive parallelization on GPUs. So as a result, most differentiable MPC methods today run on the CPU and don't scale well inside learning loops. So I think this is a bottleneck if we want to combine MPC and end-to-end learning. Imagine if we could do everything on the GPU. Then we could more easily interface state-of-the-art deep learning tools with the inductive biases of MPC and combine the best of both worlds. So the question is, how can we leverage parallelism on the GPU to solve these MPC problems in real time? Here is how standard MPC works. So MPC is often solved via sequential quadratic programming, or SQP. So SQP has 3 steps in every iteration. So the first one is that we form a convex approximation of the problem. For example, we linearize the dynamics and quadratize the cost. Then we have to solve this convex approximation, which oftentimes amounts to solving a linear system. And finally, we apply a line search, and we will iterate these steps until convergence. So steps 1 and 3 are relatively easy to parallelize. We can compute gradients in parallel over time, and the same for the line search. The key challenge for deploying SQP on the GPU is solving the linear systems, solving these convex approximations. So the second step of SQP oftentimes amounts to solving an LQR problem, the linear quadratic regulator problem. Classical solvers for LQR rely on Riccati recursions, which are sequential in time and difficult to parallelize. They work well on the CPU, but they can be slow on the GPU because GPUs are not good at sequential operations. So instead of Riccati recursions, we used recent research in GPU-accelerated MPC that was developed by the group of Brian Plancher here. And the idea is that we can take a linear algebra approach to formulate this LQR problem, and then we have to solve a linear system that comes from the KKT conditions of this LQR problem. And then if we look at the linear system, it has a block tridiagonal structure. So it's very sparse, and the sparsity is induced by the time axis. So typically we would go through the diagonal using Riccati recursions, but this is sequential. If instead we use PCG, or preconditioned conjugate gradients, then we get an algorithm that parallelizes over time. So it amounts mostly to doing matrix vector products, and these steps can be parallelized over time. And so there have been preconditioners that have been developed that make these solvers fast enough, and we can also warm start them so that we can get real-time solves on the GPU, leveraging parallelization over time. And I want to stress that there are many other parallel-friendly approaches that are starting to appear in the literature. So this is not an exclusive, exhaustive lit review. And many groups are really trying to tackle this problem of how do you solve MPC quickly enough on the GPU. So this is how you do the forward pass, where you solve the problem via SQP, and you can use a dedicated PCG solver for the linear system. Now, if you want to make it differentiable, what you need to do is implement the backward pass. it turns out that if you use results in differentiable optimization called the implicit function theorem, you can avoid differentiating through the iterations of SQP and just solve one linear system after you've converged that's defined by the gradients of the KKT conditions. So this is a famous result that was popularized by, for example, Brandon Amos at iClear in 2016, and is used widely in differentiable optimization. So what we did, the contribution was to say that if you leverage these GPU-friendly solvers for the backwards pass, you can reuse the factorizations and reuse this parallel-friendly algorithm to solve this quickly enough on the GPU and get the gradients through your MPC solver. And so this gives us a differentiable MPC algorithm on the GPU. And because it leverages parallelism, we get much faster solves than existing methods on the GPU. So in particular, MPC PyTorch and Trajax both use Riccati recursions. One is implemented in PyTorch, the other in JAX. Ours is diffMPC, is also implemented in JAX. And we converge much faster because we leverage parallelization over time. So then let's move on to the application. So we use this differentiable MPC to train MPC parameters of a drifting controller so that it's robust to puddles on the road and other uncertainties. So what we do is we randomize the simulator where we place random puddles over the figure-8 trajectory. And through a reinforcement learning loop, we differentiate through the rollouts with the MPC inside to back up gradients of the MPC to change the cost parameters and dynamics parameters of the MPC so that we get more robust performance when we drift through puddles of water. And what we found is that when you train this way, you get much fewer spinouts if you have puddles in simulation. What's interesting is what parameters the RL comes up with. So what we found was that the RL decided to decrease the friction parameters for the rear tires, which makes sense because then the engine torque values will be lower, and so the wheels will not spin as much in the rears, which means that the rear of the car will not rotate as much as we hit a patch of water, which is more robust. Also, the controller decided to reduce the costs on the side slip tracking error so that it can drift with a lower side slip, which gives it more margin for error and more time to recover and avoid spinning out. So tuning these parameters by hand would have been quite challenging, I think, and would have taken quite some time. Especially what's counterintuitive is how asymmetric the front and rear friction values are. So I think this motivates using these tools to automatically tune MPC algorithms through RL. So then, of course, we deployed it on our Toyota Supra. And these are results. Let me play it again because. So on the left, you have the controller that we tuned by hand over dry conditions, and the goal is to drift over this puddle through a circle. And so our standard method spins out because it hits the puddle of water. Whereas our method doesn't perform perfectly. It has to reinitiate the drift, but at least it keeps going and is able to follow this circle, even though there is a puddle of water. So we tried that on this circle trajectory and also through a figure-8 trajectory. So the main takeaway here is that MPC can be made GPU accelerated, and we can make it differentiable to combine the best of machine learning tools with the structure of MPC, which enables us to scale learning of these structured controllers on the GPU. So our code is available online if you're interested in this line of work and want to try the solver. I think it enables us to train RL policies to get robustness to uncertainty. And this is very valuable if we want to robustify our controllers. And I think there will be many other applications like in RL, in imitation learning, in system identification, and so on. So to conclude my talk, I showed 3 ways of using and handling uncertainty. First, we can use it to guide information gathering. Second, we can obtain more robust controllers. And third, we can use RL and differentiable MPC to automatically tune controllers and get robustness. I think there are many other interesting topics that I didn't cover related to vehicle control at the limits, like how can one condition uncertain dynamics models on vision inputs, but I'll leave that for another day. So with this, thank you all for your attention, and I'm happy to take any questions.
Thanks, Thomas. Yeah, so if anybody has any questions, I mean, feel free to just unmute and jump in, on anything. Yeah, Majid, go for it.
Great talk. I really enjoyed it. So I have a few questions on the last part mostly. So the first one is that you're building on a gradient-based optimization and try to leverage GPU. So what are your thoughts about doing sampling-based MPC instead? So which one do you think at the end would be, the winner? So this is the first question. And the other thing is that actually we already know that when you're drifting, the gradients are not great, right? During a sticky sleep or something like this, the gradient of our simulations are bad. We know that, right? It's a switching mechanism. And we know that if we do sampling, it does an implicit smoothing of the gradient to give us good gradients, right? So what are your thoughts about this product? And then my second question is that on the differentiable MPC, on the last part that you combined with RL, first, do you do a domain randomization also? Basically, do you solve a stochastic optimal control or no? It's a deterministic. Because stochasticity, I think, is very important to have a robust solution, as you said. And finally, I mean, maybe I asked one question. Maybe I can wait here.
My RAM inside my head is not.
Yeah, okay. So let's start one by one. So sampling versus gradient-based using GPU, which one do you think is
yeah, so maybe to go back in time. So the third one, here it's a standard MPC. There is no in-the-loop domain randomization. So the MPC plans with only one model, and this model is selected using RL. Then regarding gradients, so our gradients are smooth for drifting because the tire models are smooth. The challenge is that the gradients might become 0 as we saturate the tire forces. So that's a challenge because as you hit the top of your tire curve, then the gradients might be 0. Now in practice, it still works. We're able to drift our vehicles with these models. The model knows that it saturates the tire forces, so it seems to work reliably in practice. Then about sampling-based MPC, I think it can work really well. I have not compared these methods for these tasks, mostly because this works pretty well in practice and allows, enforcing constraints, inequality constraints pretty seamlessly. Now, I don't know how sampling-based MPC would work if you try to batch over MPC solvers, because if you batch, normally you already use a GPU to solve one MPC problem with sampling-based MPC because you want to maybe sample 10,000 control actions. Now, if you need to sample to solve a batch of these problems, you would need to sample 10,000 controls times the batch size. So I don't know how well it would work memory-wise, but I'm happy to, if you have a paper on differentiable MPC with sampling-based MPC, please share it with me because I haven't seen it yet. Mm-hmm. So these are my thoughts because with optimization-based methods, potentially you can use less memory and solve these things really quickly still and scale up still.
Yeah, thank you. So I had one last quick question. So you use RL policy basically to train the parameters of your MPC, right? but these parameters are constant, or they are policy. So then why do we need RL? Why can't we do Bayesian optimization or something that is a bandit setting?
You could do Bayesian. So yes, the parameters are fixed. There is work though that's starting to appear where you can train a neural net that conditions on previous driving data, and you backprop through everything. So I think it's interfacing things is possible. Now, the other question was why use RL? Oh, Bayesian optimization could work. I don't know how well it would work if you have many parameters, and how it would scale up to, if you have 20 parameters, how many simulations do you need to tune this thing? I don't know. I think using gradients makes sense to tune these things quickly enough. But of course, why not? And if you have the solver on the GPU, you can batch it and do Bayesian optimization. So it's not one or the other. Great question. Yeah.
Great, thanks.
Other folks have more questions, they're more than welcome to jump in. I see a couple videos on. Is that somebody with a question? No? Okay. I can start posing, some questions.
Sorry,
I
I
think,
did have a question.
oh yeah, no, that's fine. Like, that's great. Like, videos are cool. We can see people's faces. It's awesome. It's fun. We're all friends here. Uh, I guess so Thomas, you're proposing a number of different sort of possible approaches and directions to sort of solving this. Do you ultimately think that we need to sort of do all of these things, or is the thought more that like we just don't know enough, and so there's a number of different directions that we should sort of push on?
Yeah, so I think it depends on the task. So if you want expert level performance with low conservatism and everything to work immediately, you might need a very advanced method that combines things. Because if you just do uncertainty over control, but your bounds are too coarse, you will be too conservative and not drive at the limits, and so on and so forth. Now, for some tasks, of course, you might not need all of them. But if we build these tools, then we can unlock new applications and capabilities. So this is my thought, I think.
Yeah. And it sounds like there's another layer then on top of this that you need, which is sort of like something has to tell you how many capabilities you need for your task. And that's like but that's like a higher level thing. And what you're focused on is the lower level control primitives.
Yeah, exactly. Yeah.
I mean, that makes sense. That's also, yeah. I'm just sort of.
Yeah, we will see. It depends really
Yeah.
on the task and how you deploy these systems in practice as well.
Yeah.
I think Wilson had a question, perhaps.
Yes.
Okay.
I did have a couple questions. My first one was about your loss function for learning the Bayesian neural network.
Yeah.
So it's like log of 1 plus some kind of quadratic, I guess.
Yeah.
Sorry for making you scroll back that far.
No, this is all good.
So this loss, it looks to me like some kind of Cauchy distribution loss. Is it because you want some kind of a robust regression setting, like take care of some heavy tail behavior?
So the way you have to look at this is, so the way it's derived is through entropy and information theoretic quantities. And because the one-step predictions are Gaussian, then you can have closed form expressions of this entropy and mutual informations between what you will observe and the true dynamics. Now, I think the log, you can see it as rescaling things. The one then becomes a constant. And what matters here is that this is the uncertainty. Think of that as the covariance matrix. It's the inverse. And it multiplies regions of the state space. So like there is a transpose here missing. But you see it as uncertainty in the latent space. So uncertainty here. And it depends on where you go, because it depends on X and U.
Yeah, so that makes sense to me. So you're saying you're trying to maximize the mutual information, correct?
Yeah.
It seems like the loss function you're getting is the maximum likelihood estimation for the Cauchy distribution, some kind of multi-dimensional Cauchy distribution, which has this thing, because Cauchy distribution is 1/1 plus x squared, actually, in terms of PDF. So this is the log PDF of a Cauchy distribution.
There might be a connection to the Cauchy distribution. I've only worked with the Gaussian distribution in this setting. So great thoughts.
I think there's a connection between Gaussian and Cauchy through the mutual information thing, in a way.
Okay.
Because what you're getting is that you're getting a tighter regression, because Cauchy is a heavier tail distribution. So you're getting some robust regression kind of loss here. So I did have a second question, if I'm not being too greedy here, which is about how would you handle hard constraints in the control formulation, the MPC formulation? Because I don't think that's something that has been done on GPU yet either. I don't know anything about stochastic optimal control with constraints. Just the basic stuff about forward backward SDAs.
Oh, of course, yeah. So for these, let's see, I think, do I have a slide on this? So for the stochastic setting, right? That's the question? Yeah. So for the stochastic setting, there are different formulations that allow enforcing constraints. You can use a robust formulation where you would have every particle satisfy the constraints.
Mm-hmm.
You can have a chance constraint formulation that says 90% of the constraints should be satisfied. Then you can use CVAR, conditional value at risk, so risk-averse formulation to enforce these constraints, which is what you use here, which bounds the tail probability of violating the constraints. And the reason we like CVAR or risk-averse formulations is that when you do Monte Carlo, you end up with a problem that's as non-convex as the original problem. Whereas if you were to use chance constraint formulations, you would end up with a non-smooth problem. So during my PhD, I looked a lot at these CVAR-based formulations, and then you end up a problem that has a similar structure as the original problem, but with more variables if you do Monte Carlo. So this is one way to enforce constraints. So the robust or risk-averse formulations, I think, make sense.
So once you have this constraint formulation, you can just throw it into your, I guess, your stochastic Hamiltonian and extend the PMP through that, and the rough path.
So the PMP, the PMP is more challenging. So constraints in the PMP are more challenging to handle.
In the stochastic setting.
Because then your adjoint vector might jump in the deterministic setting. I don't know of any stochastic PMP. So I don't know any rough stochastic PMP with constraints, because this was derived last year. So
I saw your paper. You wrote it alone.
Sorry?
You wrote a paper alone on the rough PMP, I think. Yeah.
Well, but it's thanks to amazing work by all of these people who handled hard math questions before. But I don't know a method. I don't know a theory like this theorem with pathwise constraints. It would be very interesting, though. I know there are risk-averse formulations that are being developed in the cost, and they give interesting insights through the standard method, which is valuable in itself. So people are doing research on this.
And how would you go about learning the constraints if you want to extend your learning dynamics framework to learning some constraints? Sometimes constraints are also difficult to ascertain because sometimes your vision pipeline isn't perfect, your sensors are not perfect. So you might want to have some kind of latent space representation of your constraint manifold so that you can shove it in your MPC and it will behave on the real system in a predictable way.
Yeah, so I think it's task dependent. Some people study the general questions, like what if you can only sample the constraints? so through GP methods. If you constrain yourself to the racing case, for example, then constraints might be track bounds, and then it's a perception to track bounds learning problem, for example. So it might be segmentation, it might be finding these bounds, and then how do you plug it into MPC? Now, learning constraints, you don't really want to. It depends on the constraints. Some are soft constraints, right? Maybe you see that actually your engine is not as performant as you might have thought, and you can sample that. Now, if it's staying on the track, it's a hard constraint. You don't want to learn it in real time, I think. Now, some constraints might be soft. So, for example, if you drive through the track bounds a little bit, it might be fine as long as you don't spin out, right? In some places, it might be okay. So in that case, it might make sense to learn them in a stochastic way and then plug that into a risk-averse controller to, not just have hard constraints. But we haven't done that work yet. So it's going to be interesting, I think. Great questions. And anyone is free to send me an email if you have any questions.
Yeah, and anybody want to jump in with the last question? I know we're actually technically a little bit over, but I'm happy to force Thomas to answer one more question. As I said in the beginning, when my kids are screaming, he's too nice. So, he's a great guy. I don't think any more burning questions now. Okay, so let's thank Thomas again for giving a really cool talk and for answering some of our questions. And just as a reminder, we're going to have one more of these each of the next 2 months, and then we'll have sort of an event at ICRA. So I hope to see sort of all of you there. We'll send more emails. We'll post more on LinkedIn. If you have more suggestions on what the TC can be doing to better support the community, let us know. And hope you have a wonderful rest of your Thursday. Good morning to West Coast US, good afternoon to East Coast, and good night to Europe. And Asia, you're probably already asleep. Let's talk to you later.
Thank you.